Hello, welcome back to my presentation on my project for the term. This is the Fuzzy Logic and Embedded Systems dual project. So I talked about the basics of the system, and now I'd like to go into the fuzzy logic used in the system. So here we have the Fuzzy Logic Designer, which is a MATLAB toolbox, and just basically to reiterate the inputs, water temperature, pH, air temperature, and luminance. And then the controls are the heater, alarm, and light. So here are the input membership functions that took quite a bit of tuning to try and get the values that I was really hoping for. I started off with some pretty generic trapezoidal membership functions, but as I started to learn which values and outputs I was receiving, I kind of tuned them more to my needs. So here's the water temperature, and you can see the main normal range is between like 75 and 80 degrees. Air temperature is about the same, but it's a little more laxed on the edges here because it doesn't matter as much as the water temperature. And then there's pH, which is also a very strict range for what's normal. So, you know, the low range is large, and the high range is also not a good area to be. The opposite is true with the luminance. You know, basically you really can't give a plant too much light. You know, maybe up near this range it could dry it out, but there's pretty large range where it's happy, and generally this can be fine-tuned with a specific crop you're growing. For example, if you're growing corn, you're going to want it a little bit brighter versus if you're growing like something like cilantro, you won't need it as bright. So here are the outputs, pretty basic, just on-off controls for these. So the way I evaluated these was I wanted the heater to basically turn on more frequently and at different times. So that one's a little bit different, but the other two are the same, and they have identical but opposite membership functions for on and off. Now I evaluated these. If any of these values got above 0.5, I would trip the respective function to perform the action. Fuzzy rules. So for each of the outputs, there are 3 rules. So if pH is high, I want the alarm on, or low, I want the alarm on. But if it's normal, the alarm's off. And you know, water temperature and air temperature are both controlled by the heater, and obviously the luminance is controlled by the light. Moving on to testing. So I tested the fuzzy inference system by using Simulink. So I created a signal builder block. This is my fuzzy inference system, which is simulated using the fuzzy logic controller block, and then a scope block to read the outputs. So here's the signal builder block. I exercised, you know, greater than the range of the values, and I kind of did these sloping ones to really see how they react throughout the whole range. And you know, I did some quick changes like this just to test different things. So I really tried to exercise all the different outputs in this text exercise, and I also performed other tests in a method to tune the system as I desired. So here's the output. So if we go back, you can kind of see like water temperature goes up and air temperature goes up. So once both of those reach a happy point, you can see that the heater will kick off. And then when they're back, when either one of those is back out of range, then the heater will kick back on. So the heater will be on for if either one of those values is out of range. Looking at pH, we go from 0 to 10. So, our happy range is around here in the 6 and 7 area. So you can see, around this time we're okay, but when we start out we're really too low. So the alarm will be on, and then it'll kick off around here, and then kick back on, or as the values get back into the happy range, or back out of the happy range, and then as you can see, it'll kick back off and then back on again. So luminance is a similar kind of thing. You can see, that once it gets bright enough, which is around 1.6 seconds, which is like the 700 range, then the light will turn off, and then the light will turn back on when it gets out of those ranges again. So, basically here the light is too bright, so that's why it's turning off during this range. So next I tested the timing constraints of the system. So I ran my MATLAB script, and I printed out the time at each execution. So here's the first execution, and this is the values of that first execution. Oops. And you can see the time here. So 25 seconds later, exactly, the next input, and these first 4 of the inputs and these last 3 of the outputs are updated. So, here you can see there was a 1 millisecond slip, but on the next cycle, the timer gets back in sync. So obviously that's not a big deal for this type of system. 25 seconds is even pretty quick for something like this, but it's a safe requirement. Here is the writing to the server, so the ThingSpeak server, and you can see that here's the change in time between each of these iterations, and you can see that it's 25 seconds exactly for each write to the server. And here's this is water temperature, pH, air temperature, and luminance. And then I didn't carry on all the fields to make this chart look better, but you can see that they all get updated every 25 seconds. The maximum update speed is every 15 seconds. So here's the user manual. Here's the Arduino I used, and the schematic. The pH circuit, photo cell, which was used to get the luminance, water temperature sensor, and air temperature sensor. This one also reads humidity, but I didn't configure it to do that. And then the light and the heater are controlled via relays. Basically just writing these digital outputs high will trigger the relay to switch over and turn the light or heater on. So user manual of a step-by-step on how to set it up. First you connect the Arduino, wait for it to install, then just add the folder to the MATLAB path, run the script, and it will take 10 readings every 25 seconds. Here are some configurations you can do based on if you want to change the execution times or the period, or you want to add an input or an output, things like that. Here's my state-of-the-art review. So here's my system. It cost me roughly $77. I had these inputs, controlled these outputs, and had these other features. So I had the capability of controlling 67 I/O devices with Arduino, and upload frequency. So you can see that comparable system, this one has a lot more, but it doesn't have lighter and heat control, but it's $900. This was a commercial project. These other ones were research projects.